Welcome to The Explainer. So today we're taking something you literally walk past every single day, and we're going to completely change how you look at it. The common brick. I mean, it's so easy to just dismiss it as a heavy block of baked mud, right? But today we're reframing that. The brick is actually an absolute marvel of hidden engineering. It carries this rich, millennia-old historical tradition, and as we'll see, it's the foundational medium for some seriously incredible architectural art.
Okay, let's dive into this. Here is our roadmap for The Explainer. We've got 4 main sections today. First up, the anatomy of a good brick. Then, clay versus calcium silicate. Third, beyond the standard rectangle. And we'll wrap up with the art of brick bonding.
All right, Section 1, Anatomy of a Good Brick, Building from the Ground Up. 7,500 BC. No, that's not a typo. Humans have literally been relying on this foundational building material for millennia. Think about that for a second. We've been shaping the earth to build our homes, our monuments, and our cities for almost 10,000 years. But despite that incredibly ancient pedigree, modern engineering has incredibly strict standards for what actually qualifies as a high-quality brick today.
So, what exactly makes a grade A brick? Well, visually, it needs to be totally pristine. We're talking sharp, true, right-angled corners, a perfectly uniform shape, and a bright, consistent color. But it's also about physical toughness. A truly good brick should be completely unyielding if you just give it a simple fingernail scratch. And honestly, more importantly, it absolutely must have 0 white sulfate patches. That white powder, which masons call efflorescence, is caused by sulfates of calcium, magnesium, and potassium. If those are hanging around, they keep the masonry permanently damp, and that literally compromises the entire structure. A grade A brick simply doesn't allow that to happen.
To make sure these physical requirements are actually met out in the real world, builders rely on some highly rigorous and frankly very sensory field tests. First up is the 1-meter drop test. You literally just drop the brick from about 1 meter in the air right onto hard ground. A good brick is going to survive that without shattering into pieces. Next is the 24-hour soak. After you immerse a totally dry brick in water for a full day and night, it should absorb less than 20% of its own weight in water. Any more than that, it's way too porous. Finally, the strike test. When you take 2 bricks and smack them together, you really shouldn't hear a dull thud. You're actually listening for a very specific, super satisfying, clear, metallic ringing sound. If it rings, you've got yourself a solid, well-engineered brick.
Moving right along to Section 2, Clay versus Calcium Silicate, the Heavyweight Bout.
So the crucial point here is how fundamentally different these 2 materials are at a microscopic chemical level. The ratios shift drastically between them. While they both use sand, or silica, as their primary base, a calcium silicate brick relies heavily on that sand. We're talking up to 92% of its total weight. Its secondary binder is lime. On the flip side, the traditional clay brick uses a lot less sand, balancing it out with 20 to 30% alumina, which is the actual clay itself. When you add in different elements like fly ash for the modern brick, or iron oxide to give the clay brick its cohesive strength and that iconic reddish color, you start to realize that just a shift in silica and alumina fundamentally changes the brick's entire identity.
And this split in chemical identity naturally leads to 2 completely different manufacturing processes. Making traditional clay bricks is this patient, highly nature-dependent process. You have to unsoil the earth, dig it up, blend it, and then literally rely on the sun to dry the molded clay for weeks before finally burning it in a kiln. Contrast that with calcium silicate bricks. This is pure, brute force industrial engineering. The mixture is factory-pressed under massive hydraulic pressure, anywhere from 30 up to 65 newtons per square millimeter. And then it's cured inside these high-temperature steel autoclave cylinders. The difference is just stark. Instead of waiting weeks in the hot sun, a rapid chemical reaction happens between the sand and lime in just 6 to 12 hours, forming this crystal-like compound called calcium hyposilicate. So it's ancient patience up against modern engineered speed.
Section 3, Beyond the Standard Rectangle, the Language of Masonry.
Now, to navigate all those complex architectural features, masons use a really fascinating vocabulary of eccentric brick modifiers. Just listen to the charm and kind of the bizarre nature of these terms. You got the bullnose, which has a rounded angle that's perfect for when a wall takes a turn. The cownose has double-rounded corners, making it ideal for smooth window reveals. A queen closer is a brick meticulously split lengthwise, while a mitered closer is sharply cut at a 45 to 60-degree angle. And then you have bats, which thankfully have absolutely nothing to do with the animal. They're simply bricks cut across their width. So that gives you 3/4 bats, half bats, or even beveled bats with these nice angled surfaces.
These highly specific cuts are what actually allow builders to navigate tight corners, frame doors, and cap walls beautifully.
Seeing these eccentric cuts visualized really brilliantly illustrates what we're talking about here. Suddenly, these terms that sounded like a totally foreign language make perfect visual sense. Like a beveled bet creates a nice angled wedge, and a queen closer quarter is essentially just a really slender structural sliver. By studying these shapes, it's like a giant puzzle. You finally begin to see all the intricate little pieces that make up the built world around us.
Which brings us to our grand finale, Section 4. The art of brick bonding, from function to facade.
Okay, so you don't always need crazy shapes to make amazing art. Diapering is a fantastic example of this. By simply selecting bricks of contrasting colors, masons can weave these incredible diamond or lozenge patterns directly into massive wall surfaces. It's this beautiful traditional technique that transforms a purely structural, weight-bearing wall into striking geometric art. It adds immense visual richness to a facade, and they do it using just standard rectangular units.
But when builders do want to play with geometry, the results are absolutely stunning. They use classic bonding patterns to dictate the whole visual rhythm of a wall. They might start with a Flemish bond, where they alternate the long side of the brick, called the stretcher, with the short side, the header. This creates a really balanced, sophisticated look. Or they might rely on the English cross bond for a more subtle diagonal effect. If they want a bit more energy, they'll shift to a herringbone arrangement for this super active 45-degree zigzag effect. You actually see this a lot in pavements and fireplaces. And to cap the whole thing off with a strong linear emphasis, they'll use soldier courses, literally standing the bricks vertically to create rhythmic shadows, depth, and transitions right there on the facade.
But we definitely have to remember something crucial here. Decorative bonds are not just about looks. They are deeply tied to intelligent engineering and regional resourcefulness. Take that English cross bond we just mentioned. Sure, visually, it's very pleasing, but structurally, it eliminates continuous vertical mortar joints, which means the wall is far less likely to fail under stress. On the other hand, consider the rat trap bond, which was developed in India. By placing the bricks on their edge rather than laying them flat, it deliberately creates cavity walls. This totally maintains the structural integrity while drastically minimizing the amount of raw material required. It just proves that a pattern is chosen just as often for pure structural strength and material scarcity as it is for architectural beauty.
So, we've gone from the microscopic silica content inside a high-pressure autoclave cylinder all the way up to towering Flemish bond facades. It's kind of amazing, right? So I want to leave you with this final, provocative thought. What hidden patterns are holding up the walls around you? Honestly, the next time you step outside, I encourage you to look closely at your local architecture. Look at the pavements, the fireplaces, the window frames. See if you can spot a queen closer, or maybe recognize a herringbone bond. You now have the structural vocabulary to read the world around you in an entirely new way. Keep observing, keep learning, and thank you so much for joining me on this explainer. See you next time.